Thank you very much for the introduction, and thank you very much for giving me the opportunity to give this presentation and to you to come here to listen to my talk. I would like to give a kind of overview of our recent study that we've done to learn more about the sputtering from Mercury's surface into the exosphere, how this compares to micrometeoroid impacts, and what we can have as implications from the moon, for the moon. Next slide, please. So there is interest in Mercury also from the lunar perspective, because we have several very exciting exosphere observations, especially for the refractory, tightly bound rock-forming elements. For example, here's an overview of the measurements of NASA's Messenger mission of the calcium exosphere, which is highly centered around the dawn region. So this is one thing that has been interpreted, for example, as micrometeoroid related. Next slide, please. At Mercury, the interaction with the solar wind is, however, much more complicated because Mercury is a globally magnetized planet. So the magnetosphere represents an obstacle for the solar wind flow, and the interaction with the ions of Mercury's surface depends a lot on the specific location. Next, please. So as Ben basically talked about it before, we can go quite quickly through here. When an ion impacts the surface, it deposits its energy near the surface region. Next, please. And a collision cascade is formed where, next, please. Some atoms can overcome surface binding energies and be removed from the surface, which is then termed sputtered, and is an energetic contributor to the exosphere. Next. At Mercury, if you look at the global rates of exosphere sources, there is actually a somewhat unclear picture. For calcium, the messenger reported about 10 to the 23 atoms per second. Next, please. And for magnesium as well. Next. A global sputtering study that was done for about 10 years ago by Pfleger et al. Does, however, not really give us a clear image whether sputtering is an important or not important process for this. Next. There's also micrometeoroid modeling, or another one, please. Next. That gives us source rates from estimates that are orders of magnitude higher, even though seasonal dependencies and this dawn-centered emission are reproduced quite well. Next. So we want to provide updated sputter models by combining two different simulations. Next. And another one, please. So we combine global modeling, next, with a hybrid plasma code where we model this global interaction of Mercury's magnetic field with the solar wind to get precipitation maps. Next. And then we use the ST-TRIMSP3D code that Ben talked about before to model ion impacts on the surface and get local sputter yields that we then combine with our ion precipitation maps to calculate global sputtering rates. Next. So overall, because of this magnetospheric interaction, the actual flux of ions to the surface is actually significantly reduced. You get about 5 to 10% of the upstream solar wind flux impacting the surface. And if you look at the map here, the subsolar point is essentially completely shielded. Next. Because the channeling of the ions onto the surface follows mostly along magnetic field lines along these two cusps, which is also slightly asymmetric because Mercury's magnetic field has a slight northward shift. Next. This looks also very similar for both hydrogen and helium, which makes some of the interpretations of the simulations a bit easier. Next, please. We calculate from our model sputter maps, which generally look very similar to the precipitation maps. And next, please. We find that helium-2+ contributes about 40 to 50% of the total sputtering, depends somewhat on the actual solar wind conditions. And this is slightly higher than what we suspect at the moon, because Mercury's magnetosphere reduces proton energies before they impact the surface, and this is less effective for helium. Next. So going back to these rate figures for calcium, next. and magnesium, we can now calculate global rates from our modeling simply by integrating up these maps that I showed before. Next. And this gives us the red range. Again, this depends somewhat on the solar wind conditions. And you can see that it is about 1 to 2 orders of magnitude below the observed source rate for calcium. Next, please. And the same kind of or somewhat holds for magnesium as well. So we see this consistent image that the sputtering source is significantly lower than what has been derived from exosphere observations by messenger at Mercury. Next. So what is likely more happening is that basically the calcium and magnesium refractory elements that are observed in the exosphere are from micrometeorite bombardment, and this kind of a calibration factor needed for these micrometeorite models to derive how many atoms are actually removed from the surface into the exosphere. Next. However, what is also true is that, or comes out from our simulations, is that this scenario seems to be specific to Mercury. I mentioned before this reduction of 5 to 10% of the solar wind flux to the surface. If we were having unmagnetized Mercury, our rates would be much higher for magnesium comparison. Next slide, please. So these conclusions about the unmagnetized Mercury are also then important for the moon, because the moon does not have any global magnetization. And looking basically at a similar rate comparison plot for sputtering and micrometeorite and some previous modeling that has been done, we can add now the micrometeorite, the updated micrometeorite models. Next, please. Another one, please. Where we use the same type of calibration factor that I showed before that will be needed to explain messenger observations. And we get, on one hand, rates that are significantly lower than what's been estimated before. And next, please. Another one, please. And the sputter rates that we estimate for the moon are then also, again, in the same order or slightly higher than it is the case for the micrometeor estimates. Next, please. And the same holds for magnesium. There is somewhat of a question mark whether this rescaling can be applied in the same fashion for Mercury and for the moon, because it's not just the micrometeorite fluxes that are different, but also the impact velocities, so the efficiencies of certain vapor production and also condensation of molecules and even larger particles in the vaporization plume might be different. But it is a strong kind of support from the observations that we have of Mercury that sputtering is at least as important as for the exosphere production of certain elements than micrometeoroids. Next, please. Yeah. To summarize my presentation, we combined 2 different types of models to get an estimate of how important sputtering is for the erosion of the surface and transport of atoms from the exosphere, from the surface into the exosphere. Next, please. For Mercury, we find that the magnetosphere presents a significant alteration for fluxes onto the surface, changing the efficiency of sputtering, also related to energy reduction before surface impact. Next, please. We can provide updated, more, I would say, consistent estimates with observations of messenger that will support that at Mercury, the refractory exospheres are dominated by micrometeorite impacts, but because of the global magnetosphere and its shielding mechanism, this is really only specific to Mercury itself, and also when it's only exposed to the quiet solar wind. If you have a strong solar event, such as a coronal mass ejection, you would expect a change of this regime where you're back to something where sputtering is in a similar importance as micrometeorite. And this is a very exciting observation opportunity for Baby Colombo, for example. Next, please. And with this, I thank you very much for attention, and I'm happy to answer any questions later in the panel.